Okay, today we will continue with our discussions on single phase induction motors. Before we start today's continuation, I think I would like to recall what we did in the last lecture. Okay, uh, we in the last lecture we discussed the modeling of single phase induction motors. Why is it important? You know this if you look at the sheer numbers of the motors produced in the world, perhaps the largest number may be single phase induction motors. So, you find them at least about 5 to 10 in each house. Okay. You have them in ceiling fans, you have them in refrigerators, you have them in air conditioner, you have them in desert coolers, you have them in blowers, you have them in exhaust fans. Okay. So, because most of the consumer supplies or domestic supplies are single phase, and you need a motor to operate with that single phase supply. And while industrial motors are of 3 phase, because there you have a 3 phase supply, but large number of these motors are single phase. And in among the single phase supply, the single phase induction motors are the most popular. They are nearly constant speed motors, and which can drive fans, you can drive compressors, okay, and drive blowers, okay, like that. And they are used in millions, produced in millions. They are cheapest motors. So, what they typically have is, it is like a it's typical to a 3 phase induction motor, but only one winding in the stator. Okay. So, your supply is single phase. So, having 3 windings has no sense. Okay. So, you need one winding in stator, but a rotor is always squirrel cage. There is no slip ring single phase motors. Okay. So, this is the configuration. So, you have typically an unsymmetrical stator and a symmetrical rotor. Okay. Construction wise, you have a unbalanced, because single phase is an unbalance. If you want balance, you must have a polyphase, right. So, this is one peculiar situation where a single means unbalance, right. So, a person who is single is unbalanced in a way. Okay. So, the obviously the we have to understand the method of modeling when the system has become unbalanced, right. And we know that in a 3 phase machine, or it is a balance, and so long as it is provided with a balanced voltages and currents in them, it will create a very uniform rotating magnetic field in the air gap, okay. And then it is easy to analyze. You have a simple equivalent circuit, okay, and so on. Only way if it becomes unbalanced would be if the voltages are unbalanced. If the voltages are unbalanced, we have learnt that it is possible to analyze them using symmetrical components, okay. And we have two theories. One is a symmetrical component theory, where unbalanced voltages are represented as set of balanced voltages. We have what is known as a rotating field theory, okay, or a double revolving field theory, where we also say that even a single winding will create two fields, right, one forward rotating field, another backward rotating field, the same gap. Therefore, if you look at the observe from the field point of view, an unbalanced supply or unsymmetrical windings in the machine will result in more than one field in the air gap. So, air gap, there is one forward rotating field and a backward rotating field. It is as if you have taken two magnets, one you rotate in the forward direction at synchronous speed, another you rotate at backward direction at synchronous speed. Okay. So, you observe, so later you can see that that is what happens in the air gap, okay. And their magnitudes of the fields are not necessarily the same. The forward rotating field may be stronger than the backward rotating field, okay. If the forward field is stronger, it rotates forward. If the backward field is stronger, it rotates backwards, okay. So, that is so if the forward magnet is stronger or backward magnet is stronger, it decides upon the direction of torque and speed, okay. Now, if it is a single phase winding, the concept is it produces both forward and backward fields which are of equal strength in terms of stator MMF. So, stator will be subjected to a pulsating magnetic field, right, pulsating MMF stator surface with time, which can be resolved into two rotating MMFs. Now, the forward field is associated, we call it as a positive sequence, and backward field is associated with negative sequence, right. And then we also got a very subtle problem when we discussed in the last lecture, that the it is in a single phase motor only forward and backward MMFs are of equal strength, but forward and backward fields are not of equal strength, right. Imagine two fields are in the air gap, but if the rotor is stationary, okay, then reaction to forward and backward fields are identical. So, rotor surface gets also equally magnetized both to forward and backward fields MMFs. Therefore, the forward rotating flux and backward rotating flux would be equal in the case of starting only. But if it is rotor is rotating, then the reaction of the rotor to forward field will not be similar to reaction of the rotor to backward fields, because rotor will get one frequency induced due to forward field and another frequency induced due to backward field. Typically, frequency induced due to forward field will be a slip frequency SF, and frequency induced due to backward field currents would be 2 minus SF. Okay. So, the currents, when the rotor currents are different, rotor gets magnetized differently due to both fields. Look at the rotor surface, right. So, forward rotor magnetization and backward rotor magnetization of MMF will be different. Therefore, the forward flux will be different than the backward flux, although forward stator MMF is always same as backward stator MMF. I hope you understand that difference. And it was this concept which led to lot of debates and discussions several decades ago when they were trying to understand single phase machines. So, single phase machine is not a machine with equal forward and backward fields, it is only a forward and backward stator MMFs, which would mean sometimes what they said was a single phase induction motor is equal to two 3 phase machines coupled together mechanically and connecting to the same voltage source, right. But one connected with positive sequence and other connected with negative sequence. This is what was considered, but they discovered that the torque developed was not the same as single phase motor at all speeds. So, there all the problem came. If you connect them for same sequence, then the area flux for both the machines would be same, but rotating opposite way. But in actual practice, you should not connect them in parallel, you may have to connect them in series, so that the stator currents would be same and the voltages are not same. Okay. So, I think these are the things that you need to understand based on this. So, I quickly go through what we did yesterday in the last lecture. Okay. The point is, a single phase machine can be considered as a 3 phase machine with 2 windings not carrying a current, is not it. As we said, a one student in the class is equal to maybe 3 students in the class, 2 have left, are absent, only 1 is present. Okay. So, this is what it is, and so this can be analyzed using the symmetrical components, 3 phase symmetrical components, right. And so, in this case these two are not carrying any currents, right. And then I say these are the constraints, that the IBIC is 0. So, we have if this is IA, we have I naught is 1 third IA IB by C, I1 equal to I2 equal to I0 equal to IA by 3. So, this is the positive sequence current producing the forward MMF, backward MMF, and this is the 0 sequence, and all of them are equal. So, then VA is V1 plus V2 plus V0, and then VI is V1 is I1 Z1, I2 Z2 and I0 Z0, and VI is equal to VI is nothing but V1 okay, equal to IA by 3, because I1 equal to I2 equal to I0 equal to IA by 3 into Z1 plus Z2 plus Z0, right, and IA was, that means IA equal to I, whatever is the current going from the supply is the same as one going to the A winding only, because there is no current into B and C windings. Therefore, with this relation we wrote that V equal to 1/3 of Z1 plus Z2 plus Z3 into I. This is the relation we get if you use 3 phase symmetrical component with single winding only. So, we have a relation I equal to V over Z1 plus Z2 plus Z3, right. So, this is the relation we easily obtain, right, and you can sorry Z0. Okay. Then if you take the 2 phase model, because we said one student in the class is equal to 3 students are there, 2 have absent, or it is also called 2 students are there, 1 is absent, right. So, effect is same. So, there is one winding is also equal to 2 windings with this IB is 0. It can also be considered as a 2 phase balanced machine with one winding carrying no current, agreed. Okay. If, and this is the voltage, this is the current. So, this will be carrying IA and this will be VA. So, VA equal to V. So, we can say that means IA equal to I and IB is 0. Okay. So, I0 is half of what is this? I think it is half of IA plus IB. No, I think this is I1, I think. Okay, and VI is equal to V1 plus V2 and VI equal to V equal to Z1 I1 plus Z2, because this is Z1 I1, this is Z2 I2. Okay. Now, what we get is VA equal to V equal to IA by 2 into Z1 plus Z2. Okay. Right, and we also said IA equal to I, that is the winding current is same as the supply current, that is V equal to I by 2 Z1 plus Z2, right. So, we have another relation, if you use a 2 phase model, I equal to V over Z1 plus Z2 by 2. Okay. So, we have okay. Now, actually last class we clarified this. What did we clarify? See, you have two things, you say the same V and the same I. In one case you say it is equal to 3 impedances, Z1 by 3, Z2 by 3, Z0 by 3, agreed. If you take a 3 phase model, and you know what is Z1, Z2, Z0, this positive sequence circuit, negative sequence circuit and 0 sequence circuit. And another time we said the same V and the same I Z1 by 2 and Z2 by 2. This is what we get if you use a 3 phase model or a 2 phase model. So, there apparently is some fallacy, right. So, but Z must be V is same, I is same means Z must be same, no. So, this must be same as this, okay. There should be no difference. So, what we say is this must be same, right, okay. So, where is the catch? Great. So, there must be some catch here, right. See, in one case, you know what is Z1, sorry, okay. You are aware this is Z1. And this is, sorry, same thing, RR over 2 minus S, this is Z2, and the Z naught is this Z naught, okay. You are aware. And this is same RS, 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 JXLS, JXLS, JXLS. Oh, this is JXM, JXLR, JXLR. Okay, these are the things we know already. Okay. Now, the Z must be equal to Z1 by 3, Z2 by 3, Z0 by 3 connected in series, right. So, you have all by 3 by 3 by 3 into 3 by 3 by 3, right, and you connect them in series, and this is your Z, okay. And if you look at the other model, this is 3 phase model. Other model, what do we have? Same thing. Here was Z1 and Z2, okay. And this has to, this is by 2. So, it should be RS by 2, JXLS by 2, JXR by XLR by 2, RR by 2S, and here it is RR by 2 into 2 minus S. So, you connect them. So, this will be your Z, okay. So, you have RR RS by 2, JXL S by 2, JXM by 2, JXM by 2. Agreed. So, but you have one comfortable thing, this stator impedances they will match, is not it, because this will be equal to, right, this plus this plus this will be same as this plus this, there is no problem. Your problem is only with rotor parameters or air gap parameters. Here you have xm by 3, here xm by 2, okay. So, we said that when will they match, because our assumption that this XM and this XM are same is not true, okay, and this RR are not same, right. Why? I made a statement. In order that these must be identical Z, this Z must be same as this Z, right. You have no problem with stator resistance, because whether it is a 3-phase motor, 2-phase motor, the resistance of stator winding must be same. If this measure 2 ohms, that must also measure 2 ohms, right. Just because you do a different modeling, you can't make change. Leakage reactance stator is also same. So, that you have got satisfied. So, the sum of these, this plus this plus this will be same as this plus this, okay, no problem. So, you got in both cases you have stator impedance is no problem. This is the equivalent circuit we get. RS, JXLS. Okay. Now, only thing is in one case you get XM by 2, another case is XM by 3. You have RR by 2, RR by 3. So, the only thing is, see, RR in 3 phase divided by 3 is equal to RR in 2 phase divided by 2. So, you need the rotor resistance in both models are not same, because you must recall what is known as 3 phase to 2 phase transformation. You have done this 3 phase 2 phase transformation. So, there is a factor of 2 by 3 comes to picture. Okay. So, your rotor is a multi phase winding squirrel cage. You can refer to 3 phase or 2 phase or 4 phase or 6 phase or 8 phase, but the per phase resistance will not be same. So, that is the reason why you have a different value. So, with this because we normally single phase machines always usually use a 3 phase mode, we normally, this is a general practice. So, we have this, that means you have RR by 2S, RR by 2 into 2 minus S, and this will be JXM by 2, this will be JXM by 2, and this is JXLR by 2, this is JXLR by 2, where rotor resistance leakage reactance is also referred to a 2 phase mode, right. So, this with this clarification we proceed. That means you can represent the voltage Vs and the current Is in the stator winding equivalent circuit, and this is ZLS, right. ZLS will be RS plus JXLS, right, ZLS, and plus you have a one is ZF by 2 and ZB by 2. What is that ZF? So, ZF is this is ZF, which is JXM RR by S JXLR, this is ZF, and ZB is same thing, this is JXLR RR by 2 minus S, that is all, okay. This is JXM, this is ZB. So, we call this as a forward impedance at the air gap, this is forward impedance, we call this as a backward impedance. That means, you are standing on the air gap looking into the rotor, that is what it means due to the forward field. So, this voltage that is coming across here is the voltage due to the forward field induced into the stator winding. This is the voltage due to backward field induced into the stator winding. So, you have this will be EF voltage due to forward field, EB voltage due to backward field. okay, and this will be ZF by 2, because you know that everything is divided by 2 here, okay, everything divided by 2. Therefore, it is ZF by 2 and ZB by 2. Okay. So, our ZF is as per the 3 phase mode. Okay. So, now what will be the power fed from to the forward field PGF, sorry, okay, right, PGF is what, just like in a 3 phase machine, it is IS square into RF by 2, okay. So, forward field, just like in a 3 phase machine, how much power is fed into the air gap is whatever is the resistive component of the air gap impedance, right, and PGB is IS square into RB by 2. So, you are feeding that much power to the rotor from the stator through the air gap. Now, you are giving power to the forward field and power to the through the backward field. Okay. Now, the forward field will produce a torque Tf is Pgf by synchronous speed, backward field produce a torque Pgb by synchronous speed, right. Therefore, this, but at starting Tf equal to Tb, at starting both are same, because this Rf equal to Rb at starting, because S is equal to 1 at starting. So, both impedances will be same, ZF equal to ZB, Rf equal to Rb. So, S equivalent, so therefore, single phase induction motor does not have a starting torque, that is what we have seen. Okay. So, we have this sorry, ultimately we get these currents and then we do the calculations and use this equivalent circuit, right, and this is how you do calculate the performance, right, and the torque forward will be equal to 1 over omega s I R f square R r by s, and torque backward is 1 over omega s I r b square R r over 2 minus s, right. So, that is what we will get, the torque developed in a single phase motor. And we also said that in view of this, you have a curve, you have the forward torque, right, and then you have the backward torque, and you can have the net torque, right. Right. So, what you observe is there is no starting torque, and the 0 torque at there is at 0 torque is not at synchronous speed, it is less than synchronous speed, and there is a maximum torque which is not at the same point. So, you have a slightly less torque, because there is certain negative torque also being injected at the normal place. So, this much torque has to be compensated. So, a single phase motor tends to be rated less compared to a 3 phase motor, because it has to compensate for the negative torque, these currents at the additional current due to the additional rotor currents due to the backward field, right. So, there is extra rotor heating due to this without producing any useful work, okay. Right. So, now let us take a 2 phase symmetrical induction machine, asymmetrical. You see most of the motors are 2 phase, but supply is single phase, right. And I hope you know that ceiling fan motors, there is a auxiliary winding where you put a capacitor there, and auxiliary winding leads the main winding, okay. So, it is a 2 phase winding. So, you have, if you say the main winding and auxiliary winding, sorry, of course, he has written main and auxiliary. Okay. So, A leads M by 90 degrees electrical, and this is squirrel cage. And these two are asymmetrical. What do you mean by asymmetrical? The two windings, but they are at 90 degrees, at least to some extent that symmetry is met. What other asymmetry will be there? What? But while designing, what do you make? And the making, how do they make it? Why make? What is it asymmetrical? Number of turns will be different. So, the thing is, this may have Nm, this may have Na, and Nm equal to not equal to Na. And they may be done, they may have a different gauge wires. So, the resistance will be different. So, resistance of main winding is not the same as resistance of auxiliary. Leakage reactance will be different. They are wound differently. They can have, okay. So, they are asymmetrical to that extent. Okay. Now, I think we have to slowly, I will have to take you through a very very tough path now. Okay. So, you must understand the concepts very clearly. Now, let us say I do not energize the auxiliary winding, I only put a current I m in the main winding. So, let us assume that there is a current I m in the main winding only and auxiliary winding is dead. What will so I have applied a voltage V m and I am passing a current I m. Then what will happen is there will always be a drop due to ZL, let us say due to this is the M main winding impedance, and then it will produce a forward field and a backward field, is not it? After all, single winding, it produces a forward field and a backward field and give you a forward voltage and a backward voltage. I think there is no problem, because as we did in the single phase machine. So, and that impedance will be that EF is proportional to Im into ZF by 2, this will be Im into ZB by 2. So, this will be the voltage forward. So, the voltage what you apply will be the voltage due to the leakage plus this. So, Vm will be equal to VLm plus EF, let us say M plus EB M, is not it? Is it clear? So, the field will induce a voltage in the winding, stator winding, which is being compensated by the supply voltage. So, KVL will work, right. Now, that field which is inducing that voltage in the main winding will also induce a voltage in the auxiliary winding, is not it? It induces a voltage, how much it will be inducing? In the auxiliary winding, the same forward field which was producing EM in the forward field will produce, it is ahead, therefore, it will be J times that voltage in phasor position. Okay. Since it is ahead, it will be J times that, and now the thing is that it is A winding is having A is Na by Nm, the turns ratio, because they are the auxiliary winding is A times more than the main winding. So, the voltage will be A times that, okay, into whatever it was producing in the main winding. Main winding it was producing Im into Zf by 2, okay. What it was producing, because we have A is Na by Nm. So, EMF, the forward voltage is Im into Zf by 2 and backward voltage is Im into Zb by 2, and of course, this ZLm is equal to R of the main winding and Jx of the main winding. Now, it will induce in the auxiliary winding with this turns Na by Nm, it will have, sorry, okay. So, we have EAF equal to JA IM into ZF by 2, EAB is equal to minus JA. In due to backward field, what will happen? It will be minus J, because it is rotating other way around. So, minus J, but voltage A into I same, but it will be ZB by 2. Is it clear? Therefore, both forward and backward fields in the air gap will induce voltage in the main and auxiliary winding. Forward field will produce EM forward and EA forward, and backward will produce EM backward and EA backward, which would mean, see, if there is a forward field, okay. So, in the windings you may say EM forward, where will be EA forward, leading or lagging? Leading. So, this may be right, because this is not same, because A times, right, this is due to forward, and the backward is, supposing there is a EM backward, and that will, where will it induce? EA backward. Is it okay? This is due to backward. I hope people will not criticize me for always talking forward and backward, right, with political sense nowadays. Okay, right. So, this I hope you understand. There is a forward field and the backward field produce different voltages. Okay. Now, now let us consider that you have only IA is excited. Okay. So, I do not excite the M. So, IA is excited. Okay. So, it will so EA will be EA forward. So, IA will also produce two fields in the air gap, two fields in the air gap, and one will be, that will be IA into ZF by 2, because the same ZF which is referred to the main winding. All our parameters are referred to main winding, okay, to avoid confusion. So, rotor refer to main winding, auxiliary refer to main winding, okay, so that you have easy to handle it. But now, since the A winding is having more turns, so the voltage is proportional to A square, because the flux MMF is increased and flux is increased, right, while the voltage is proportional to flux and the flux is proportional to current. Okay. So, if you increase the current, if more turns, the flux will be A times that. Okay. Therefore, it will be A square. If the main winding 1 ampere produces a voltage 10 volts, in the auxiliary winding 1 ampere will produce more volts, because it is wound with more turns, right. Okay. Therefore, EA backward will be same IA ZB by 2 into A square. Right. Okay. If you pass a current IA in the main IM in the main winding, it will produce a voltage V. Okay. Now, if you pass the same current in the auxiliary winding, right, it will produce an MMF which is proportional to A times the main. That means, it will produce a flux, air gap flux, which is A times that one, and that flux will produce a voltage which is again A times. What is voltage? 4.4 Fn into Fn into, so N also gets A times, phi also gets A times, is not it? So, both the flux has increased and turns have increased, right. So, there is cumulative effect of that. So, it will be A square. Now, you imagine that there is a forward field which is inducing a voltage in the A winding like this much voltage it is inducing because of the current IA passing through it, induced voltage. Now, that field is not keeping quiet, it is also inducing in the auxiliary winding, in the main winding. This is the auxiliary winding, it is inducing in the main winding. The forward, if this is producing this much in the forward field in the main winding, which is main winding incidentally is lagging the auxiliary winding by 90 degrees. So, it will be minus j, right, okay, and it is not having the same turns as this. So, it will be EAF by A, right. So, it is not A square, it is A into IA into ZF by 2. Whatever is this voltage, that will be, so the magnitude of this will be EAF by A, is not it, because it is less turns, is it clear? And this the same now the EAB, if the same field is producing a voltage in the auxiliary winding, it will produce a voltage in the main winding which is ahead. The backward field, for backward field the main winding is ahead. So, it will be J times A into IA into ZB by 2. Okay. So, now imagine that just due to backward field, there again voltage is induced both in the main and auxiliary winding. There are 2 voltages in the main winding, 2 volts in the auxiliary winding. If you excite a main winding, it will produce 2 voltages in the main winding, 2 in the auxiliary winding. If both are excited, you cumulative by superposition, is not it. So, if both are excited, there is a voltage due to forward field due to main, voltage due to backward field due to main, and voltage due to forward field auxiliary, etc. So, we can always sum it up. So, if both of them are excited, my main winding is excited with the current IM, auxiliary winding excited with the current IA, then what will happen? The induced voltage in the main winding will be the EM forward due to main winding, EM forward due to auxiliary winding, EM backward due to main winding, EM backward due to auxiliary winding, right. So, there are 4 induced voltages in each winding. Okay. Then okay. Now, what is this EM? EM forward is ZF by 2 into IM, and backward is minus JA into IA, is not it. So, this is this, right, okay. And EM backward will be, we have already done it, ZB by 2, because these two are proportional to ZB by 2. So, and this is the EM backward is proportional to IM, and EM backward is proportional to, I mean this is A is IA, okay. I mean, we have derived that anyway, I hope you understand. So, this is the almost like a cumulative forward MMF, this is cumulative backward MMF, right. They are producing this, this one, this one, no, no, what is EMB? Is ZB by 2 IM, no? Oh, we have to go back. See, what is EMB due to main winding? See, EMF due to main winding is ZF by 2 IM, and this is ZB by 2 IM, that is all, no change. Therefore, similarly, that is due to the voltage induced in the main winding. Now, what is the voltage induced in the auxiliary winding? Will be same EAF due to main winding, EAF due to auxiliary winding, EAB due to main winding, EAB due to auxiliary winding, right. Similarly, so your EA, the net voltage induced in the auxiliary winding will be due to the forward field of A I A, which we already derived this. This is due to this, that is A square I A plus J A I M, because this is this current, okay, E F auxiliary. Then this will be Z B by 2 A square I A minus this. Okay. I think you have to verify this, right, yourself. I think then you will understand, and also you should be convinced about this. Therefore, but that is the voltage induced in the windings, but what you apply is not the same voltage, right. What you apply, this applied, you apply a Vm which is whatever induced plus there is a resistance leakage reactance drop, that also will be there, no, okay, is not the air gap voltage. So, Vi is Za IL plus Ea, is it okay? This is applied voltage, right. Now, let us denote what is known as the forward voltage, that is Vsf is half of Vm minus j Va dash, just like your positive sequence. I define a forward voltage which is just like the forward field will produce a set of voltages, we will define this like this. I make it as j Va dash, because after all there is a Vm, and if it is a balanced system, then Vm must be equal to Va dash, is not it, only due to forward field. So, I call this Vsf is half of Vm minus sorry, this is no, actually this should be Va dash and this will be Vm, sorry, because this is leading. So, that is Vm minus j Va dash, okay, and Vsb is half of Vm plus j Va dash, okay. If it is purely balanced, then it will be other way around. So, I call this is definition. Similarly, you define ESF is half of Em minus j Ea dash, and ESB is half of Em plus j Ea dash. I am defining these quantities, and ISF I call it as half of Im minus j Ia dash, and ISB is half of Im plus j Ia dash. What is Ia dash will be A times Ia, is not it, right, and sorry, and that what is Va dash? Va dash is Va by A, like a transformer turns transformation. You refer to these turns, okay. So, earlier it was higher turns, now you reduce it to smaller turns. So, it has to be divided by A, okay. So, our definition of turns is Va dash is Va by A, Ia dash is Aia, and any impedance transformation is Za dash is Za by A square. I hope you know this, right. Therefore, from this set of equations, we have Vsf, that means you have to sum up all these things, right. Vsf will be ISF ZF plus ISF ZLM by 2 plus ZLA by 2 A square, and plus ISB by 2 ZLM minus ZLA by A square. And VSB is ISB ZSB, this is the backward, ISF ZLM by 2 minus ZLA by A square plus ISB by 2 ZLM plus ZLA by A square. Now, I want you to verify this, because sometimes I have to give some work to you. So, you verify this, right. I mean it is algebraic summation, but you have to do it so that you are convinced that what we have done is right, okay. Now, I have defined a term called ZD, which is the ZL A dash minus ZL M by 2, because you have this term ZL A by A square. Okay. This is ZL A by A square, ZL A dash minus ZL M by 2. Okay. So, with that sorry. Okay, this is a new definition, I call it as a shunt impedance ZD. So, what you have with this, you can get VSF is equal to ISF ZLM plus IF ZF plus ZD into ISF minus ISB, and VSB is ISF ZLM plus no, I think it is ISB, please make the correction, VSB is ISB ZLM plus IB ZB, this is also wrong, plus ZD ISB minus ISF. So, please look at these two equations purely from circuit point of view. There are two currents, ISF ISF and ISB, right, is not it? Here what are the two currents, ISF, ISB, and two voltage VSF, VSB, right. So, you can easily write a circuit out of this, right. So, how does it look like? So, you can always say I have a VSF and I have an ISF, and then we came to know that there is a ZLM, right. Then you have a ZF, right, and then you have a ZD. Agreed? If you look at the last, so you have ISF, ZLM, ZF and ZD, they are in, all the three will be there in series. So, that is a loop impedance as far as ISF is concerned, but there is also a minus ISB ZD. Okay. So, the ISB will flow like this, other way around. Okay. So, if I write the back other circuit, this will be VSF and this will be VSB, okay. And what do you have there in that circuit also? There also it is a loop impedance will also have ZLM, right, and it will also have ZB. Okay, and ZD. It satisfies, this loop will satisfy both these equations, right. ISB ZLM, ZB, ZD minus ISF ZD, right. So, I hope it is very simple. Okay. With so much of complicated arguments, we will end up in a very simple circuit for you. Okay. And where ZD is what? What is ZD? ZLA dash minus ZLM. Okay. Now, what is VSF plus VSB? Because this is the voltages, you know. What is sum of these two, VSF plus VSB? Is nothing but V voltage at the main winding. Okay. So, that is the voltage at the main winding. And that is VSF to VSB, and what will be this current here, ISF minus ISB, what will be that? I think it is JA IA or something, let me check. Yeah, minus JA IA. Okay, that is auxiliary winding current. Okay. So, we have this circuit VSF, VSB, ZD, ISF, ISB, ZLM, ZLM and ZF and ZB. Okay. So, it is clear. Now, we will have a easy to write VSF this is RS M J XS M, I mean XLS M J XLR, okay, RR over S is not RR by 2S, it is ZF actually, right. So, big JXM, sorry, this will be ZD and this is VSF, VSB, and please note that this is not auxiliary, it's both are main winding only, JXLSM JXLR RR over 2 minus S JXM. So, this will be ISF ISB, and we have what is most important is ZD will be ZLA by A square minus ZL, let us say M. Okay. Now, what is important is the for different machines the ZLA may be different, auxiliary winding you may connect some capacitors also, is not it. So, see ZLA there will be something for split phase, split phase only R and X, right, and for capacitor machine you have a connecting capacitor also, and so capacitor would be that will be its R A plus J X L A minus J X C, because you are connecting a capacitor. So, that is also you have to include in the analysis, right. And then another thing is what you have you need to understand is that normal motor, normal single phase motor, what happens? Voltage you are applied to the main winding is also same as voltage you apply to the auxiliary winding, they are connected in series, connected in parallel. So, you have the main winding auxiliary winding connect the same voltage source. So, you connect them like this, main and auxiliary, right. So, this also you must know the constraint. So, VMF VFB will be there. So, we will close quickly. So, we have the you can calculate the same torque is twice IF F square RF, that is TF, then PGF is twice IF F square RB and TB is this. So, you can find out the forward and backward torque now that you know what are the currents in the windings after solving for the currents. Okay. So, the torque will be TF minus TB is 1 over omega s PGF minus PGB. So, this will be the net equivalent torque. So, we know how to analyze a single phase motor with single winding and two windings. In two windings you use this circuit, calculate the stator and rotor currents and positive torque and negative torque or a forward torque or backward torque, and you are able to get the required characteristics of the machine, whatever the torque characteristics you can have. There will be a forward torque and there may be a backward torque. So, the net torque will be a sum of these two, which may not be, you can create a non-zero starting torque at this point. Okay, we will stop it here and we will continue in the next class. Thank you.